Much of what we learn in high school physics is ruled by small little scratches of our pencils or markers across the page. These little scratches are vectors. Vectors are abstract ways of showing values related to the movement of objects or forces acting on an object. The main thing to know is that vectors are arrows. We need to know that the arrows point somewhere and they have a magnitude, an amount of something. These two aspects about vectors are what make up the definition. Any quantity of value that requires both magnitude and direction is a vector. You will draw many vectors in Physics 30. Basically, using vectors helps us to be able to calculate much of the stuff that we need to calculate in physics. Much of the understanding around motion and forces, the ways of showing how we can fly, drive, throw a ball, sled down a hill, keep satellites around the Earth. Pretty much any of these things, anything we've engineered, has involved working with vectors. So here's my pro tip. Work with them. There's really no shortcut. You will have to find your way to truly understand and apply the skills of working with vectors. You'll have to draw them at scale at times. You'll have to use a ruler. You'll have to add them together and subtract them. You'll have to know how to break them down with trigonometry. That's important. You know that guy Pythagoras and his theorem? I sure hope so. You remember the sine law? How about the cosine law? Soon you'll be experts in breaking down vectors into component parts. But let's back up a little. I want to take you through a few notes about vectors from this book, The Theoretical Minimum. It's written by Leonard Susskind and George Hrabovsky. The book contains what they figure is the absolute minimum that you need to know to study physics. I'm going to pick out a few details from the book that I think you should know for high school physics. Let's start with the origin. Setting a good origin makes things easy to figure out. The origin is the starting point for our work with vectors and our work with objects. Really, the origin is arbitrary. It's a personal choice. But this is the key. Wherever you pick as an origin, you need to keep that spot as the origin. So what are some examples? If we were to look at the nature of movement of planets in the solar system, we would pick the sun as our origin. It's at the center, and all the planets revolve around it. What about kicking a ball? The origin would be that point of contact. With the dropping of an apple from a tree, where might you consider an origin? Probably at the point of release. See? Arbitrary. Actually, arbitrary might not be the right word. The starting point, center of something rotational, these are good origin points. Axes. No, not axes. Axes. Think of all the time you've been drawing graphs in mathematics over the last few years. You may have even been asking, why am I doing this? Well, physics is a great place to use graphs and the coordinate systems that go with our graphs. This is where our origin comes into play because it's that 0, point in a graphing system. Susskind and Hrabovsky talk about working with 3 axes, x, y, and z. But for our work, we can mostly consider just x and y, 2 dimensions. But here's a rather arbitrary choice. Where do we put our axes? Well, thinking generally, our x-axis is the horizontal axis and it goes left to right. Positive values to the right, negative values to the left of the origin. The y-axis is the vertical axis. It has values going up and values going down. Negative values below the origin, positive values above the origin. As we progress in this course, Physics 30, the x and y axes will always be perpendicular to each other, but they may need to be placed at different angles in the system to work well with our vectors. Hence this arbitrary decision of orientation. The axes allow us to assign a location with coordinates to things like the origin and where the object ends up. That allows us to show forces with magnitude amounts in various directions that we can then calculate using trigonometry. The axes allow for direction and magnitude of vectors. But we need one other thing when working with most calculations involving vectors: time. If you want to get fancy, you can consider time as a fourth dimension, x, y, z being the other three. Working with time is much like working with a direction. There's forward moving time, which has a positive value, and backward moving time, in which the values are negative. Our time measurements usually have a starting value, which is commonly 0. Whatever you do, make sure you pick the appropriate units for your measurements of time and direction. But time. Usually for physics, our time is in seconds, though you'll have to handle some conversions along the way. Don't worry, you'll do great. Wonderful. So we have our vectors figured out with direction and magnitude. We have some usage of time. Now we have all we need for our reference frame for the object. As it moves through time or space, we can calculate the motion of the object or the forces acting on the object. With that, we can do all sorts of physics. Still a little confused? Sure, you might be. It's good to have a little theoretical background that we don't quite understand. The important thing is that we consider how vectors are helpful for calculating values, and that at this point we can start visualizing or showing how vectors are represented in various situations.